So I wanted to run through titration curves and a couple of examples because of questions that came up today in office hours. And obviously there's a lot of you that are not attending or can't attend, and I wanted to hit this point as it seems to be an important one to make. I also want to make sure everybody knows it is absolutely in your best interest to come to office hours, really try to make an effort. Even if just to put in an earbud and listen to the conversation, it can be very helpful. A lot of times what you'll kind of realize is the stuff that you're struggling with is something that a lot of people are struggling with. And so a lot of the same type questions are being asked. So you can find that really helpful and certainly save you some time in terms of studying. I also had some students that just requested that I try to post more videos of me talking to y'all, which I don't mind at all. I have to balance this because some of you feel like it's too much information and it's overwhelming. So again, sometimes no matter what I do, it's not going to make everybody happy. But if you like these videos, great, listen to them. If you don't, it's not a problem. You don't have to. Do what works for you. So this is a titration curve for alanine. And when we look at alanine off the bat, right off the bat, y'all should remember that the side chain is a methyl group. This is a more hydrophobic amino acid based on side chain characteristics. And we know that it has two pKa's. One is going to be associated with the alpha carboxylic acid that at pKa of 2 will start to ionize to form the carboxylate. And the other pKa of 9 is due to the alpha amino group that will also ionize going to the conjugate base form. Now, when we look at titration curves, you draw a titration curve. Always set up drawing out the box here. You want to put on the x-axis your OH equivalents that have to be added. And you're going to put the number of protons that are ionizable. So since alanine is a diprotic amino acid, that means it has two different protons that can be ionized. So I'm going to need two equivalents of hydroxide added in order to force ionization. Then what we have are at the 0.5 marks, we're going to put the pKa's that are inflection points. So I'm going to put my first inflection point. We say this is about 2. I'm going to put my second inflection point, and we say this is about 9. So that's the numbers you're going to memorize. Yes, I know these vary. Clearly, alanine's is a little above 2 and just below 10, but we're just looking at average values for calculation so that we all use the same numbers and get the same exact calculations for quizzes and exams. So this would be 2 and 9. So as I go ahead and draw that out, I would look then at my titration curve. So this is the titration curve that I have drawn. This is for alanine. On the x-axis, I have my OH equivalents. They're going to have to be added. You see the 1 and the 2 because of the fact that this is a diprotic amino acid. And then I'm going to mark the pKa values of 2 and 9. Just asking, what is pKa going to be due to? Protonation state that we're going to see reflected by the alpha carboxylic acid. This is a low pKa because this is an acidic group, and the name carboxylic acid. Then we have pKa of 9. This is going to be due to my alpha amino group. This is more basic, thus its pKa is going to be higher. So when we look then at which of the different forms of the amino acid are going to be predominant in solution based on pH. So make sure you know how to draw this titration curve, and now we're going to go back and we're going to look and see which amino acid ionic forms are going to dominate at which of the pH ranges. So if we are at a pH below pH 2, this means that we are below the pKa's of 2 and 9, and both of these functional groups are going to be in the acid form. So the cationic form is going to predominate. We call it the cationic form because it carries a positive charge due to the amino group, and carboxylic acid is neutral. So that means this carries an overall net charge of +1, and this means that it's a cation. Now, as we get above our pKa 1, which is equal to 2, we start to see an ionization event. What's happening? In this case, what we start to see is that the carboxylic acid group is going to give up its proton. And we're going to see our HA form, and again, at pKa 2, we only care about this group. we're going to see that it's going to go to its conjugate base form. Then we get to our second pKa value. So we've hit our equivalence point. All of the carboxylic acid has ionized. It's in the carboxylate form. And we start hitting our next pKa. What starts to happen? Our amino group starts to ionize. So it's going to give up its proton to solution, and we're going to hit our second equivalent point. So what happens in this case is, for a diprotic amino acid, at most acidic pH, when all protons are on, it's going to be its cationic form. When we have all protons off, it's going to be in its anionic form. And in between the two pKa values, this is where we're going to see the Zwitter ion. Now, what's significant about the Zwitter ion? This is where it has no net charge. So in the case of the Zwitter ion 0 species, net charge 0 species, we can average the two pKa values and give us an idea of the pI, which is 5.5. So hopefully that makes sense to everybody, but I want to take it one step further. And I want to ask the question, what happens to the net charge when we are at a pH value that's equal to a pKa? So the example here with alanine, let's just say that we want to ask, what is the overall net charge at a pH equal to 2? What is this going to look like? So I've written here, we have our pH is equal to 2, and I'm asking what the net charge is. When pH is equal to 2, we know that we are around the ionization event that's dealing with our alpha carboxylic acid. When the pK is equal to the pH, what do we know? That the concentration of acid in solution is equal to the concentration of its conjugate base. We're dealing with carboxylic acid. So for every one amino acid molecule that has an alpha carboxylic acid, the other molecule is going to have the alpha carboxylate, which means that the proton has already ionized. One HA for each A minus. So the next part is what does that mean in terms of net charge? Well, we have half of the population that's going to carry a +1 charge. Why? Because the amino group is +1, and my alpha carboxylic acid group carries a no net charge, neutral. So that means +1 + 0 equals +1. So we have an overall +1 charge for this molecule. This makes up half of the species. The other half of the species are going to be in the conjugate base form. What's its overall charge? 0, +1 for the alpha amino acid, amino group, and -1 because our carboxylate is formed from the ionization of a proton. So we have a -1 charge. +1 plus -1 equals 0. So if we want to know the overall net charge at pH 2, when these two species are equal in solution, what would the charge be? It would be the average, so +1 plus 0, and then we divide that by 2 is going to give us a positive 0.5 charge. So we would have molecules with a half charge in terms of the population. So you could also ask yourself what's going to be the net charge when we look at pH equal to 9, based on the fact that the pKa of the amino group is 9. See if you can work that out. You can pause the video if you need more time. But what would the charge be? It would be -0.5. Why? Because when the pH, and I'm going to put this part in blue, is now equal to 9, we already have ionization of our carboxylic acid group. That's not changing. In this case, what are we looking at? And we'll put it again in blue. Our amino group is what we become concerned with. So what does this mean? At pH 9, my HA population is going to be due to the alpha amino group being protonated. pH 9, I'm well above my carboxylate group being able to ionize. It's already in the conjugate base form. pH 9, now we're looking at the acid conjugate base dealing with our amino group. So my HA forms protonated alpha amino group. My A minus form is the deprotonated amino group. So what's the charge going to be? Now what do I have to do? I have to look at the fact that my HA form is now 0, my Zwitter ion, and my A minus conjugate base form is now -1. If I look at the average of that, now what do I have? HA form, overall net charge of 0. A minus form, -1 charge. I'm taking the average of these two species because they're both present in equal amounts in the population, and now my overall net charge is negative 0.5. If these help, I really don't mind doing them at all. Hopefully that does. I had a number of questions about that on titration curves today. Make sure that you know your amino acid side chains characteristics. Those are going to be very important. We're not going to get away from that this entire semester, so you want to make sure that you know those. And everybody remember that you have your quiz, and it has to be taken during your designated lecture time. So sections 509 to 512, you're at 11:30 to 12:45, 20-minute quiz. Make sure you get that scheduled. And for those of you that have class from 1:30 to 2:45, you're going to see sections 517 to 520 that are going to pop up. So keep up with the class. Let me know if you have any questions, and I'll talk to you all soon.